Okay, y'all, we are finally on the last page of midterm 1. It's definitely taken us longer than 2 hours, which is the allotted time, but we're explaining everything, and it's okay. So, the first question is asking you to write a systematic name corresponding to the molecule below. Let's just draw this in the regular way, because it's not really important that we see the chair confirmation for this. Call that one 1, 2, 3. 1, 2, 3. NH2. And we've got this isopropyl group. Okay, so I forgot it too. So the amine takes the first priority. So we're going to have amine at the end. We don't have anything else that's not just a regular alkane. So the amine takes the first priority. There's only one carbon group or hydrocarbon group attached to the amine. The others are hydrogen, so that's going to be part of the priority with the amine, and it's a hexane or cyclohexane, right? Because if it was just a straight line, or you know what I mean, 1, 2, 3, 4, 5, 6. If it was just like that, that would be a hexane, but this is in a cycle, so it is a cyclohexane. So it's going to be cyclohexane amine as our main part of the molecule. It's the main part. And then we have to name the substituent. The only substituent is the isopropyl group right here. It's not a regular propyl group. That would be just, that's not true. Propyl is just 3 carbons in a chain, but this is 3 carbons but in like a foot shape, right? It's still 3 carbons, but yeah. And it's not part of the main chain. The main chain is the cyclohexanamine, so it has to be named as one substituent. So it's called isopropyl. Isopropyl. And what is the number of the substituent? Well, I actually didn't mean to number it like this. I was just numbering it to draw it in the other way. But we're going to number so that NH2 is the lowest number. So we're going to start with the carbon that's attached to the NH2, and that's going to be carbon number 1. And now we're going to go around the ring. We can go in either direction, theoretically. We could go in this direction or in this direction, depending on what the substituents are. But we are going to find that this one that I drew is going to be the preferred one, because then this will be number 2, this will be number 3, 4, 5, and 6. Versus if we went around this way, this would be number 2, 3, 4, 5, and 6. So our one substituent, isopropyl, would be on number 5, which we don't want that. We want lowest numbers, and so we want our one substituent to be the lowest number that it could. And so we're going to go the black way, where the numbers are lower, where we go around. Let's just erase the red. We want to go around so that the isopropyl has the lowest number while still making the carbon attached to the amine number 1. So that's going to be 3 isopropyl. Cyclohexanamine. So the 3 represents where the isopropyl is, and then the cyclohexanamine is the main chain. Okay. So we already did what we did above. That's kind of like what we did here, except they called this one 1, 2, and 3, and this one is 1, 2, 3. So Since the NH2 is going up, it's going to be a wedge on 1. And since the isopropyl is going down, it's going to be a dash on 3. Okay. We can't figure out the equilibrium arrow until we've calculated delta G. Oh, actually, that's not necessarily true. Well, we have to draw the substituents on chair B, and then let's see if we can figure it out. If not, we have to calculate delta G first. And negative delta G is favorable. So if delta G is positive, that means it's going to be mostly going towards the left, and a little bit to the right, because we want delta G to be negative, so we want it to go in the reverse direction. And if delta G is negative, then it'll be mostly going to the left, or to the right, and a little bit going to the left, because we want to proceed in the direction where the delta G will be negative. Anyways, okay, so for chair B, this is number 3. And so NH2 is up over here. So it still has to be up on number 1 over here. But because number 1 is a down carbon in chair B, you can draw like a down arrow like we did before for the other page, the last page. Since it's a down carbon and NH2 is an up substituent, we are going to draw it down or draw up at an angle, and it's going to be parallel to this line, the line from 2 to 3, and the line from 4, 5, the line from 5 to 6. So that's going to be the line leading to the NH2. And then number 3 was the isopropyl substituent, and it was going down, and now 3 is a down carbon, so it's going to be down here. So either way, we have one kind of bulky group, the NH2, the amine group, going axial in chair A, and then we have the isopropyl going axial in chair B. So both of those are unfavorable. We have to figure out which one is worse by calculating delta G, or which one contributes to the unfavorability, I guess, if that's a word. And so I copied the information that was given to us on the first page with the energy differences. That was just on the first page, is on a little scratch paper sheet. And so we're going to use that to figure out delta G here. So we're going from NH2 being axial to equatorial for chair A to chair B. So we're going from chair A to chair B for our delta G. So that means it's a favorable one. So that's going to be, for NH2, we're going to take the number that we find below and we're going to subtract that for delta G, because we're releasing energy. That's a subtraction. We're going from axial to equatorial. Every time we go from axial to equatorial, that's going to be favorable. Yeah, we just prefer that. So right here it says 1.2 is the energy difference between axial and equatorial, so we're going to subtract 1.2 to lead to our delta G. And then this is isopropyl. We're going from equatorial to axial. This is equatorial, this is axial. So that is unfavorable. So we're going to add whatever value we find down below for isopropyl. So what is isopropyl? It is an R group, and then it's, so this carbon right here, it has an hydrogen, and then these carbons each have 3 hydrogens. We need to write that out because that's how it's going to be written here. And so that'll be this one right here, because it's CH and then 2 CH3 groups. That's exactly what we have here. This is the CH, and then these are the 2 CH3 groups. So we're going to add 2.2. So those are just the part of delta G that contributes to, or that is contributed by going from axial to equatorial for our substituents. We're not really going to count the hydrogens going from axial to equatorial because there's a whole bunch of them, and that's not really important. There's 2 on a bunch of these, and then there's 1 on this. It would altogether even out. So we're going to look at the rest of the instructions. It says, assume that every additional Gauss interaction adds 1.0 kilocalories per mole. So there are no extra Gauss. That would be like if we had another, technically there is Gauss between this and like the 2 hydrogens that are on here. There's like Gauss here, but that's not like an additional one because the isopropyl will also have a Gauss hydrogen here, and those are just like not as significant. It would altogether even out because there'd be an extra Gauss here with the isopropyl and the hydrogen, and then there'd be an extra one over here with the NH2 and the hydrogen. So altogether it evens out. So this is not relevant for this part. And then it says assume that every additional 1,3 diaxial interaction sorry. Assume that every additional one adds 0.5 kilocalories per mole. So let's pick apart what this says. It says 1,3 diaxial interaction. So that would be if like 1 and 3 both were axial. But as you can see, like over here, 1 is axial for the NH2 and 3 is equatorial. Over here, 3 is axial, 1 is equatorial. So this doesn't apply here. When would this apply? This would apply if we had drawn our flat ring wrong, or if we had done something wrong so that we had like, let's just draw this in red. If like somehow we were like, oh, 1 goes from up here to down here, then H2. That would be when we'd have a 1,3 diaxial interaction. And so we would add 0.5 kilocalories per mole into our delta G. But that's not the case here. That shouldn't be the case. If you did do that, you should probably be consistent, and that would go into your delta G if you did make that mistake. But hopefully you don't make that mistake. So you don't have to worry about it. So the delta G, we're just literally going to add these numbers because that's all we have. So it's 1.0. It's positive. That's not favorable, so it's not mostly going to go to the right. It's going to only go a little bit to the right, and it's mostly going to want to go to the left. The left side is more favorable. Okay, so this is something I still get a little bit confused about. So this one is asking whether they are constitutional, configurational, or conformational isomers. I call them the 3 con isomers. They're a little easy to get mixed up. So let's see if I get this right. So for the first one, that's constitutional isomers. I think of this as like different to their constitution. Like everything's different, you know? I mean, obviously not everything because they're isomers. So isomers means that there's the same number of each atom. I'm pretty sure that's like all an isomer is just like the same number of each atom. There's still the same number of carbons. There's still the same number of oxygens. Whatever. But it's constitutionally different. Like they can be arranged to different things. There could be an oxygen connected to a carbon, and then connected to another carbon versus like a carbon and an oxygen, or like they could be totally different. And that's not the case here, because well, you could go around and number like 1, 2, 3 versus 1, 2, 3. Either way, there's like an isopropyl on the 3rd carbon, and an NH2 on the first carbon. You could also name it like 1, 2, 3. It doesn't really matter. Either way, they're like 2 carbons apart, and it's still like a cyclohexane as the main chain, so it's not going to be constitutional isomers. Those are super different. Okay, conformational isomers, the last one. Those are when sigma bonds rotate. So conformational isomers basically would look the same if it wasn't on a chair projection. These are actually called conformers. Conformers. So if we were to just draw them out, they would look identical on like the regular like cyclohexane rings. They would look the same. Let me see, what does configurational isomers? So this means these are super different. Connectivity. These are rotation of single bonds. So I'm going to look it up on my phone real quick, what configurational isomers are. Because I think it's just when, like, R versus S. I think it's when it's attached. Here, let me just look it up. Configurational isomers. Yeah, there's stereoisomers. What does it mean for this case? Oh, okay. Okay, so, so if it was configurational isomers, since we haven't learned R or S yet for this exam, it would be like, so since this one is up for the NH2 and down for the isopropyl, and this one's up for the isopropyl and down for the NH2. Those aren't configurational isomers, but if it was like NH2 is up here and then everything else stayed the same, then that would be a configurational isomer. Basically, like if the wedges and dashes switch. Here, let's draw on these normal ones, not the chair conformations. So this will be the blue one, and this will be the green one. So let's call 1, 2, 3. NH2 is going to be up, wedged, and isopropyl is going to be down. And then so we can call 1, 2, 3. NH2 is going to be down, and isopropyl, oh, nope, it's going to be wedged. So, actually, if you like flip this molecule over, let's erase this. If you flip this molecule over, imagine you're like on the piece of paper and then you just like flip it over. Then we'd end up with this one, where the NH2 now, oh, NH2 now comes out at us because we flipped it over. Before it was going into the page, now it's going out of the page, and the isopropyl over here. Let's move this over a little bit more so that we're not getting our two isopropyls right next to each other. It's a little confusing. Put that right there. And our isopropyl is right here. So as you can see, the blue and green are now the same. They look the same on here. But we know that like if we were to really like flip this over, it wouldn't be exactly the same because the NH2 would still be equatorial and this would still, the isopropyl would still be axial if we were to flip it over. But they look the same on these projections because they're just the rotation of a single bond. So that's what makes them conformational isomers. Okay. Yeah, let's go ahead and draw the two cyclohexanes for this one. So we'll call this one green. We'll call, well, here. So this one over here will be green, and this one will be that kind of indigo color. If we name like 1, 2, 3, then it'll be 1, 2, 3 here. This will be wedged for the NH2 because it's coming out of the page. And it's going up on the chair, and the 3 is the isopropyl. It's going down. Let's call 1, 2, 3, so we're not getting our numbering switched. And the isopropyl, oh wait, no, we want the, we want 1 to be on the NH2. And we want to go towards 3 for the isopropyl. So NH2 is going into the page. The isopropyl is coming out of it. So let's flip this green one over this way and then rotate it so that number 1 is where number 1 is there. Or actually, we don't need to flip it. We can just rotate it so that number 1 here is where number 1 is on the indigo one. 1, 2, 3. H2 and isopropyl. Nope, that'll be wedged. So as you can see, these are not identical when we're drawing them in the regular way, in the cyclohexane way. I guess they're both cyclohexane ways. Anyways, they're still not the same because the stereochemistry is switched. They're not constitutional isomers because they would have to be constitutional if like they were one for their part. Like either way, there's still one carbon between the carbon that the NH2 is on. So there's one carbon between the NH2 carbon and the isopropyl carbon in both of these. So they're not constitutional isomers because they'd have to have different connectivity or different atoms connected to different things. And that's not true. They're not like different from each other. If like the isopropyl was over here, that would be a constitutional isomer. They're not conformational isomers because that would just be a rotation around a single bond, and that's not true because if we draw them this way, we can still see, like if you flip it over or something, then the isopropyl group will be over here instead. So yeah, either way, those are not conformational because they are, they're actually enantiomers of each other. I don't know if we had gotten to that part yet in the class, but basically we can't superimpose them onto each other, and so that's when they're configurational isomers. Because, I think configurational, the way you think of it is it's the same atoms connected to the same substituents, or it's the same atoms connected to each one of each other, but they're rearranged in space. So let's just write that down. So constitutional means different connectivity. So that means, I did something wrong. I'm tired. That means that there's different atoms connected to different atoms, basically. Still the same number of each atom, but they're just connected in different ways. They're totally different. That's not either of the ones above. Configurational means that it's a let's see. It's still connected to the same atom, but it's connected to a different spot. So, different arrangement of same atom connections. I don't know if that really makes sense, but you know, getting the idea across. Conformational is just rotation of single bond. That's like the Newman projections too. The different conformations of each other, the rotations of the single bonds. Okay, so that is the end of midterm 1 for Chem 3A. Hope that you learned something.